Hello, everyone. This is part number 3 of the complex number lecture series that I have been developing. And in this part, I'm going to go over uh, complex numbers in the form of transfer functions. Transfer functions are basically used in engineering in different fields of engineering, electrical engineering, mechanical engineering, and other field of engineering. And basically, what transfer functions are, they are the ratio between a system's output to its input. And generally, we they are a function of complex variables. So generally, they're represented in rectangular form as a ratio or in division, basically in terms of division. And most of the time when we are studying the transfer function, we are studying the magnitude of transfer function as it is changing with respect to the variable that they're function of, and also the phase of the complex variable of the transfer function as it changes when we change the variable of the function. So many times I have seen students again struggling with transfer functions for no reason, because again, think about them as um, a fractional form of complex number given in rectangular coordinates. And then you can convert them into polar form, and from polar form, you can, of course, have the magnitude, you can have phase. The only difference is it is a function of a variable. It is not just a number as 2 plus 3i or 5 plus, 6i or 6j, but it is given in terms of variables. So I think that's where the confusion is usually. So in this short video, I will try to give you some examples of different transfer functions from um, different classes that we have in engineering, circuits class, signal processing, control systems, and so on and so forth. And then I'll show you how easy it is to interpret those transfer functions and how to write down the polar form, the magnitude and the phase from the rectangular form. So let's go ahead and start. Let me go ahead and share this screen. Okay. So as a first example, let's say we have a circuit, and I'm not going to go into circuit analysis over here, but let's say we have a filter. Filters are circuit that let some frequencies go through them and stop other frequencies. So let's say we have a filter, and the output of the filter is given by, it's a function of complex frequency, as you can see, j omega. Omega is frequency, which is called the angular frequency. Units are radian per second. And let's say the output of the filter circuit is given by 1 over 1 plus j omega r c times the input of the transfer function. Now, the transfer function from the input and output relationship can simply be given by h of j omega. J omega, of course, is a function of j omega right here, is the ratio between the output and the input. And output is a complex number, input is a complex number, generally given in polar form. Input is usually given in polar form. And that is equal to 1 over 1 plus j omega rc. Now, what we, in circuit analysis, let's say, what we need to observe is how the transfer function magnitude is changing and how its phase is changing when you're changing the value of omega. When it is going from 0 to a higher value, how does this change? So the question is how you're going to write down the magnitude and the phase of h of j omega. Now observe that this is given in what? Rectangular or Cartesian form, right? It's given in rectangular form or Cartesian form. Now, from the rectangular form of any complex number, whether it is given just a plus jb or it is given in fractional form, if you remember from our previous lecture, if I want to write down the magnitude of this from its rectangular representation. How do I calculate the magnitude of a number that is given in fractional form, a complex number that is given in fractional form? Remember, it is the magnitude of numerator divided by magnitude of the denominator. So since numerator is simply a real number, the magnitude is just going to be 1. And the magnitude of denominator, if you remember, a plus jb, the magnitude is calculated as square root of a squared plus b squared. So simply 1 squared, which is 1, plus b squared, which is omega rc. Do not include j. I have seen people making mistake and write down j omega rc squared. So there's, you don't calculate magnitude. You don't consider j while calculating magnitude, or you don't consider j while calculating the phase either. So this is the magnitude response of the transfer function, or just simply the magnitude of the transfer function. And as you change the value of omega, this magnitude is going to change. Observe that when omega is 0, the magnitude will be 1. And as omega increases, then the magnitude is going to decrease. So this is basically what we call a low pass filter. It let low frequencies go through it and it stops the high frequency. Observe that magnitude becomes very large, denominator become very large, and omega become very large. Then the denominator is going to become very large, and the magnitude is going to drop down to, or is going to approximate to very small number, and eventually it's going to become 0. What will be the phase of this? If I want to write down phase, now remember, phase of a complex fraction is phase of the numerator minus phase of the denominator. So here phase of the numerator is 0 because this is a real number and it is located on the positive x-axis. So this is the real, this is negative real. It's a complex plane. This is imaginary number on y-axis and negative imaginary number of negative y-axis. So this one, of course, is right here. That's it. So angle of that with respect to the positive x-axis is 0. So the numerator angle is 0 and the denominator angle is calculated as tangent inverse of b over a, as we discussed in the previous lectures. So tangent inverse of omega rc over 1, or simply omega rc. So the phase is simply negative tangent inverse of omega rc. So as omega will increase, starting from 0, the phase is 0 initially, and as omega is going to increase, then the tangent inverse is gonna go from 0, and since it's negative here, so it's gonna go from 0 and it's gonna travel through different angles. And when omega rc becomes quite large, then the tangent inverse of very large number, asymptotically it tends to 90 degrees. So it's going to be, in this case, it's going to be negative 90 degrees, of course, because we have a negative sign here. So the phase is going to change from 0 degrees to negative 90 degrees. And you can plot it by changing the value of omega. And perhaps in the next part of this series, in the 4th lecture, when I will be showing you how to use MATLAB to manipulate complex numbers, then I will show you how easy it is if you have a transfer function, how easy it is. You don't really have to do any calculation. All you need is a transfer function expression. And from that, we have functions in MATLAB that you can calculate the magnitude, the phase, and then you can plot it very easily. So I'm going to show you that in the 4th lecture, as well as it might be helpful to many students taking different engineering classes. Now, if you're not an engineering student, perhaps this lecture may not be very useful for you. So you can stick with the first 2 part of the lecture where I discuss the basics of basics of complex numbers and the arithmetic of complex numbers. But this is one of the examples. Let's show you another example. So the next example, let's look at another let's assume again another circuit example. I'll give you a little different transfer function. Let's say the output is equal to negative 2 omega RCL, and RCL is resistance, capacitor, inductance. If you are in taking a circuits class, then of course you should know about it. If you're not, then you don't have to worry about it. Let's say I have 1 minus omega square RL plus J omega RCL. Let's say this is a transfer function times, not transfer function, sorry. Let's say this is the output written in terms of transfer function. Remember, this is a transfer function, which is the ratio between input, output, and input. So again, if I want to calculate the magnitude of this transfer function, remember, is the magnitude of the numerator. In this case, magnitude of the numerator is simply 2 omega RCL, right? Magnitude means length, remember. So negative is not going to be part of the line. Negative just represent that this point is located on the negative real axis. So somewhere over here, negative 2 omega RCL. But this length represent the magnitude of H. And that length is simply 2 omega RCL. So that is the magnitude of the numerator, and the magnitude of the denominator is, again, it is a complex number written in rectangular form. So A square, A is 1 minus omega square RL. A square, 1 minus omega square RL square plus B square plus omega RCL square. So that's the magnitude of this transfer function. And likewise, the phase of the function. Phase of the numerator minus phase of the denominator. What is the phase of the numerator? It is located on the negative real axis or negative x-axis. That means from the positive x-axis, the phase of any number on the negative side is 180 degrees. So anytime you see a negative real number, the phase is 180 degrees for that. And then the phase of the denominator, which will simply be again tangent inverse of B, which is omega RCL, over A, which is 1 minus omega square R. So that will be the phase of the transfer function. And again, you can plot it for different values of omega. And it's gonna start with 180 degrees. And this, when it will become too large, of course, then tangent inverse of a large number is going to be 90 degrees. So it's going to go from 180 degrees to 90 degrees when omega becomes very large. Or actually, in this case, since we have omega in numerator and denominator both, so when it will become very large, we can ignore 1 over here. And it's just going to be a tangent inverse of a negative. If you take the limit of this, it's just going to come out to be tangent inverse of a like a -1 or something, so 45 degrees. So it's going to go from 180 degrees to whatever the angle is going to be, and we can easily plot it. But anyways, so this is the magnitude and this is the phase of the transfer function. Now, if you are required to calculate, let's say, the value of the output voltage, let's say, the value of the output voltage for any value of the input voltage, then remember the input voltage is multiplied by the transfer function. This is the transfer function. So at any frequency omega, to calculate the magnitude of the output voltage, you first calculate the magnitude of Hj omega, which through this, formula or through this expression, and then you calculate the magnitude of input voltage at that frequency, and you're going to multiply the two magnitudes to get the magnitude of this. Now, to get the angle of V out J omega, remember, if you're multiplying two complex numbers in polar form, then their magnitudes multiply and their angles or phases add together. So you're going to calculate the phase of this at that frequency, and you're going to calculate the phase of VI at that frequency, and you're going to add them together to calculate the phase of the output voltage. So keep that in mind. Give you another example. Let's say we have in control systems, let's say we have a transfer function given as HS is equal to S square plus 4S plus 5 over S cube plus 6S square plus 7S plus 8. All right, what is S? S is the variable of Laplace transform, and it's generally given by sigma plus j omega, where sigma represent the transient variable. So how when a system is changing, when it starts, when it go through a changing phase, then for a brief amount of time, there's a phase called transient phase in which it is still settling down to its final condition. And then omega represent the frequency of oscillation. So let's say it has been settled down. So all the transients are gone, and we assume S is equal to j omega. So if we put S is equal to j omega here, like we did earlier, then that's going to be j omega squared plus 4j omega plus 5 over j omega cube plus 6j omega squared plus 7j omega plus 8. Now to simplify this, j omega squared, remember, is what? J squared is -1. So that's going to be negative omega squared plus j4 omega plus 5. That's the numerator. And the denominator is going to be j omega squared is negative omega squared multiplied by 1 more j omega because it's a cube. So that's going to be negative j omega cube. J squared is -1, and then negative 1 times j is negative j. Minus j omega squared is negative omega squared, so minus 6 omega squared plus j7 omega plus 8. So let me rearrange the terms. Make sure whenever any number, any complex number is written in rectangular form, always rearrange the term to show real part plus j imaginary part, whatever is that. So I'm going to rearrange the top term. I'm going to write down as 5 minus omega square plus j4 omega. So that's going to be real term a plus jb divided by denominator. Let's say what I have 8 minus 6 omega square plus j, I'm going to keep the j as common factor of 7 omega minus omega cube. So that's the denominator. Now, if you want to calculate the magnitude of this, then it's simply the magnitude of the numerator, which is the square root of 5 minus omega squared plus 4 omega squared divided by magnitude of the denominator, which is 8 minus 6 omega squared a squared plus b squared. That's going to be the magnitude of this transfer function. And the phase of the transfer function we can calculate similarly. That is the phase of the numerator minus phase of the denominator. So phase of the numerator is tangent inverse or arctan 4 omega over 5 minus omega squared. Tangent inverse of b over a. And phase of the denominator is tangent inverse b, which is 7 omega minus omega cube divided by a, which is 8 minus 6 omega squared. That will be the expression for the phase of the transfer function. So this is pretty much what, a brief introduction of transfer function, and when a transfer function, and pretty much all the time transfer functions are given in rectangular form, in fractional complex number rectangular form. And most of the time we have to figure out what is the magnitude at some specific frequency or the variable of interest, and what is the phase at the variable of interest or frequency. So this is how you can calculate the magnitude, phase, and then plug in the value of omega and other variables and determine the actual values at a specific value of frequency or the variable of interest. And you can plot it again, as I said, using any utility, plotting utility. I will show you how to do it in MATLAB in the next lecture. But I hope this lecture would have helped you understanding transfer functions, or at least giving an introduction of transfer function. And hopefully, if you're taking any class in which you are using transfer functions and you see a complex variable, then I hope that it will help you with that class. So I will see you in the next lecture.